Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, our topic is electrical current. So far, we've taken a look at capacitance and how to store electric charge. We took a look at electric fields and how they, different charges, anything with an electric charge generates an electric field, which causes movement of these charges. But how do we actually use that to power our devices and to power our lights? We're going to take a look at that today in what we call electrical current. We're going to take a look at how to quantify current, the direction of current, what we call drift velocity, and then lastly two things that might affect your current. So let's jump into it. First of all, electrical current is how much charge passes through a certain area in a given amount of time. And so here I have this equation that represents that. A pretty simple equation. I, being the electrical current in amperes or amps, is equal to the change in charge, or delta Q, the charge passing through that hole or that wire per time or per second. How much charge is passing per second. So if I have a large amount of charge passing through every second, I'm going to have a large current. Or if that charge passes really quickly through that wire, then again I'm going to have a very high current. And vice versa. If the charge is moving really slowly or have a very small amount of charge, my current's going to be very low. And so as for the direction of current, the charges that are moving in a wire could be positive or negative. In our devices, mostly they are negative electrons, and so the direction of the positive charges, however, is what determines the direction of current. And you'd think that we would kind of use the same direction, or the electron movement as the same direction as a current, but we do not. We actually use the opposite. So the current direction is always opposite to the flow of electrons. So let's say my electrons are flowing through this wire here. My current's actually going to be in the opposite direction. Same thing for if I have a circuit. If I have my battery and the electrons are moving in this red fashion, okay, because they're negative and they're moving towards the positive end of the battery, my current is actually going to be moving in the opposite direction. And so the current is largely generated because of the movement of these charges. And so what we have what we call drift velocity, which is the net or the sum velocity of the electron moving through whatever tube. Because although we have an electric field that causes this movement of the electrons, most of the electrons move something like this. They go boingy, 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 all the way through the tube, and then straight again. And so, unfortunately, our electrons don't move just straight ahead, and so the magnitude of these small little velocities are the magnitude is very small for these velocities. And so what we do is we have a net velocity, and we call that the drift velocity. And that is kind of the sum of all of these velocities, all of these vector velocities. So although I might have a current of 10 amps going to the left, the electrons are only moving a very small velocity because of this really disorganized movement. So moving on to the two things that might affect your current, one of them is this thing called resistance. Resistance is like the word says, is the opposition generated by the against the electric current, and usually it's because there's a device that's using that electricity. So like light bulbs have the resistance. Also, every single type of wire we have has a certain amount of resistance. Resistance can also be used to control the current, because sometimes we don't want too much current running through our device because it might break it. So we can also use what we call resistors, to regulate that. And so the four variables that affect resistance and hence current are length, area, material, and temperature. And so notice, in terms of wires, when we're transporting electrical current, we want the least resistance as possible. And so how do we do that? Well, we want to make the length short for our wires. So if I have a wire that's really short, it's going to have less resistance than a wire that's very long. So the longer our wire is, the more resistance our electrical current is going to face in the wire. Also, the cross-sectional area. So if I have a very thick wire, okay, my resistance will be a lot less. Copper has one of the least resistance. That's why we use it in our our wires to transport electricity here in the United States. And then of course the lower the temperature is, the less resistance we get. So we want to make it cold, short, a large cross section, and made out of copper. And as you can see, vice versa gives us greater resistance if we wanted to have greater resistance. And so here's kind of a diagram that displays that better. Less resistance. How do we get that or attain to that? Short length, large cross-sectional area, made out of copper, and then at a lower temperature. And lastly, the other thing that might affect our current is salt water and our perspiration, because you might be thinking, well, when I touch the Van de Graaff, for example, does that have a lot of current, or like does that have a lot of voltage? How come that doesn't kill me if I just touch it and I get zapped? But how come that doesn't happen? Well, because of your skin and the properties of your skin, you have layers and layers of dead skin and layers and layers of cells. It generates a very large amount of resistance, 500,000 what we call ohms, which we'll look at next lesson, when it's dry. However, and this is why they tell you to not, when you drop an electrical appliance that's on in water, you shouldn't touch it because your resistance is going to go way down and you'll get electrocuted. When you are wet or when you're soaked in especially salt water, your resistance can go down to 100 ohms and electrical current can go right through your body. And so what we call that being electrocuted, of course, when electrical current moves through your body, and it can be very dangerous. A current as small as 0.15 amps could kill you. And then lastly, perspiration can, when you sweat, you also release ions that can conduct electricity, so your resistance also goes down and makes you susceptible to having higher current run through you. And so that's why lie detectors use that to their advantage in determining if you're lying, because when you lie, or when you are nervous, you'll start to sweat, and these detectors on your body can pick up this decrease in resistance or increase in electrical current that can run through your body, and that's how they can tell if you're lying or not. That's one way they can tell. So that's really cool. That's current in a nutshell. Thank you so much for joining us, and we'll see you next time.